Right, if we could get ready for our feature presentation. So I have been friends with Aisha Scott for probably 3 years or 4 years at this point. And she is the person that I have run into in the most different contexts in the area. So whether it's history events or sort of gourmet events or boating events or astronomy events, we keep running into each other. So I was really excited when she we kind of offered to trade talks. So I'm going to give a talk about Umberto Eco to her Italian group, and she's going to tell us about some camera lenses that were used in the Apollo program and also used later by Stanley Kubrick, and sort of some of the most exciting lenses ever made. So Aisha graduated from Marygrove with a BFA in art. I think she's going to tell us a little bit about that. Her interest in astronomy began with astrophotography. She got her first digital camera at the age of 12 to document family vacations. Though she doesn't currently work in the art field, she continues to maintain her passion for photography as an enthusiast. So without further ado, Aisha Scott.
Thank you. So tonight, just a play on words, a giant leap in lens design. I will be talking about the Planar Lens that was used during the Apollo project. Maybe not.
Oh, is it?
There.
Yeah, just the
Arrows? Okay. Okay, so who am I? My name is Aisha Scott, BFA in art. So I got my bachelor's concentrating in graphic design from Marygrove. My background in photography, I'm not a professional photographer. I have worked, done a little bit of professional photography, mainly associated with graphic design. So when I've been commissioned to do a work, if they don't have very good photography, I volunteer. So I've done both. I've worked with both film, traditional photography, including lab work and developing in the lab, and also digital photography. I own a crop sensor. I'm a Canon person. If you know anything about cameras, there's Canon and Nikon are the main brands. I'm a Canon person. And how I got interested in this group particularly was I was interested in astrophotography, which is super hard, and it's its own discipline in its own right. Just as a disclaimer, I am not a scientist. I am not a professional photographer. As far as this presentation goes, a lot of this is more of like investigative journalism style rather than actual fact. A lot of this is my own speculation, partly because the fun thing about the Planar is that there are no official necessarily documents on it when it comes to NASA. The way I had to go about this was I had to look for the information that wasn't there. There's a lot of information on cameras, but mainly the information on cameras was for the television cameras that were produced for Apollo and for the satellite cameras that were produced for Apollo. This is something different, it's unique, it's a still camera. It was mainly for documentation, the photography that you see in magazines, things like that. So just that disclaimer. All right, so I'm not going to make any assumptions. I'm just going to cover a lot of broad things. The first thing I'm going to talk about is actual light, because that's what a camera records. It records light. So the basics of how light works is that a light bounces off of an object and into your eye. Okay? So this is recorded in lux. If you look on the paper, there's different measurements. It's you're probably more familiar with that AB reading. as far as the moon goes. But I just wanted to show you this as a comparison of how much light the moon actually gives off and how hard it is to photograph the moon. So a strong sunlight gives 100,000 lux. Full light's day, that's around noontime, will give you 10,000 lux. An office light, like this building, would give you 500 lux. A poorly lit room gives you 100 lux. A light bulb gives you 60 lux. And the Earth, I'm assuming that number comes from actual space, because you can't photograph the Earth while you're on the Earth, gives you only 30 lux. And then the moon gives you about 0.5. So the amount of light that bounces, comes from the sun and bounces off the moon is, for the average camera, is super hard. The moon is horrible to photograph with your average camera. So the reason why the Planar was developed as a lens was that you needed a lens that could let enough light into a camera in order to photograph the moon with such a small amount of light. That's what makes this lens super special. Alright, so how a camera works. The camera works a lot like an eye, right? So a light bounces off an object into your eye. Your pupil opens and closes to let more light in and out. Your retina is like your sensor or your film that records the actual light. Alright, so this is the actual parts of a camera. To give an example, you see the light coming in, you see the mirror. The mirror is not too important. What the mirror does is that when light comes into a camera, it shows flipped, it shows backwards. So the mirror actually flips it so that the film can record it. And then you have your film and your shutter. I'll just go that. So, okay. So your sensor is what's recording the light. So digital cameras they're based off of traditional cameras. They use the same language. ISO is the sensitivity of the actual film. So 1600 ISO is going to be twice as sensitive as 800 ISO. The average film for ISO is about 400, 400 speed, as you would say. Your shutter is your exposure time. So your shutter works like a window, letting light in and out. Your average for a day might be only 1/100th of a second is how much your shutter is going to open and close. Your aperture works a lot like a pupil, right? If you're in a dark room, your pupil opens wide open to let more light in. In a bright sunny day, it gets smaller to let less light in. And then your lens. So lenses are measured in millimeters. 50 millimeters is going to be considered eye, what the human eye is most comparable to. Anything above 50 is considered a close-up lens, and then anything below 50 is going to be considered a wide-angle lens. This is important because the Planar is a 50-meter lens. It's considered, in artistic terms, it's more personal because it's what the average person would be viewing the world looks like. Alright, so what is the Zeiss Planar lens? It was invented in 1966 during the Apollo program. There's actually 10 lenses ever made. Ever. That's it. It's not a commercial lens. Zeiss has one. NASA had 6. And then later on in the future, the future slide will talk about what happened to the other 3, because it's actually really special what happened to the other 3. The aspect ratio is 0.7. So I have it's an older camera. I have a crop sensor camera. Crop sensor is about this, a full-size sensor is similar to about a 35 millimeter camera. I have a crop sensor, so maybe about half is what my crop sensor represents. It's an older camera. It's a Rebel 4, which is a lower end Canon camera, but it does the job pretty well. The average ratio for my camera is going to be like 5.6. That's the aperture of my camera. To explain the numbers, the higher the number, the smaller the hole for your aperture. The smaller the number, the bigger the hole, the closer it is basically to 0, which would be the full window of the camera, actual camera. Average aperture for even professional cameras, and we're talking about cameras, lenses that cost like $5,000, usually only go to about 2. This is a 0.7. This is ridiculous. It's considered to be one of the fastest lenses ever invented, and this was in 1966, and it's still pretty much, other than you're talking about light, regular light, not infrared or ultralight, it's still pretty close. I think the closest thing is a 0.4 nowadays, and this is, we're about 50 years later, and that would cost you a good $10,000 nowadays. The focal length I said is 50. The lens mount, so this is really special. This is a very special lens mount. We'll talk about the camera a little bit later in a future slide. What's important about these specs is that, like I said, there's no actual official document from NASA that actually names the Planar camera in the documentation. What does happen is they name the specs. They name the camera. They name the aperture. They tell you the size of the lens they're using. They never tell you the name of the lens. So what happened in order for me to get this information is I had to scrub the data from different articles and make assumptions that based off of these specs and what cameras were used, what mission this actual lens was used on. So that's why these specs are really important. They're really unique because there's not another camera that has a 0.7 aperture, or even comes close, and or uses that shutter. It was manufactured in Germany. So Zeiss is a German company. They are the premier company for lenses. They are #1. They started out making microscope lenses and moved into camera lenses. And yeah, the lens now is worth about $23 million. If you find one at an antique, you'd be hitting the jackpot. All right, so who is Zeiss? I talked about it a little bit more. Carl Zeiss founded the company. It was founded in Jena, his headquarters in Jena, Germany. So how it started out getting into camera lenses is that it was forced by the Nazis to design their infrared lenses on their warheads. That's how they got into lenses. So what's special about that actually is that the United States saved the plans for this particular lens. It was a top secret type of thing from Germany, and Allied forces in a special operation called Operation Paperclip actually saved the plans for this lens and helped Zeiss, get under the thumb of Nazis, basically. All right, so what cameras use it? So this is a unit camera, the Hasselblad 500 camera. It uses this special shutter. The shutter was ahead of its time because it's electric. It's one of the first electric shutters. It's faster than every other shutter. And basically this is a commercial camera. And the unique story about how NASA started using commercial cameras was one of the astronauts for the scouting mission for the Apollo, which is either Gemini or Mercury, probably Mercury, he went on family vacation in Europe and bought a camera overseas in Germany, because it's available in Europe. It wasn't available in the United States. He bought that camera and brought it back, same way like you would go to a science conference and think it's a cool conference, decide to bring your home camera to document everything. He did that for space. He took his own camera into space, brought the pictures back. NASA saw them and got the idea to use commercial cameras to go into outer space in order to document what's going on. All right. So before I head to the next slide, I was going to ask this question. All right. So who in this room knows who invented the car? Anybody?
Yeah.
Oh, you guys are nice. Who's usually who? Okay, so when you ask that question, who usually people say? Who do people think invented the car?
Henry Ford.
Henry Ford. Right. So what did Henry Ford actually invent?
The assembly line.
He invented the assembly line. So this is what I think about inventors. If you want to die poor, invent something. If you want to die rich, invent the process that is used to make that thing. And that's what Henry Ford did. He made it faster. He didn't invent the car, he just made it better and faster. So that's what happened with this lens. This lens is designed by Dr. Erhard Gotzel. All right, he is the Michael Jordan of the lens design, basically. And this lens is the first time Zeiss ever used a computer to design a lens, ever. That computer cost in 1966, it cost $1 million to just, and you're talking about $1 million in order to design 10 lenses. That's it. So this is the first time a computer's ever been used. There's 4 prototypes. I'm going to talk about that a little bit, maybe further on when we get more into the design of it. There's some special things about the actual design. Okay, so we'll go with that. So what is the design? The design is a double gloss style lens. It's expensive to produce based off of the glass that's used. Flint and crown glasses are used to make this lens. It has a Zeiss T coating, which is a special coating that helps with sharpness. They still use T coating on lenses. It's the same exact coating on most of the newer lenses. And then it has a zebra type finish, just meaning it's black and silver. It's kind of important that it has a certain finish because it makes it more easier to identify. So, like I said, I had to go scrubbing for information. And one of the things I did is I went online to the Smithsonian's archives and actually looked at individual pictures. And the one thing I noticed about Zeiss lenses is they have the zebra finish. They're black and silver. It made it easier to identify. So that's why it's important. So this is the actual design. Yeah. And this is 1966. Like newer lenses have like a good 15 different types of lenses. I don't know how much we want to go into this right now. If you, I passed out some different terms that will help you with the lens. Gauss, what Gauss style is, what a double lead is, all these different things. We could go deeper into this and I'll explain the lens. This portion right here to here is the actual planar design. This right here is a little bit more special. I go into that when we get into the history. But that's what the lens actually looks like. Alright, so what's the design history? The Pirzar lens invented by Joseph Pirzar. The Smith field flattener invented by Smith. So okay, so this is a picture of what what an image with the Pirzar lens looks like. And one of the things you notice is the distortion around the edges, right? So what that distortion is caused by is you have to think. The lens is a circle, the image is a square. So what happens is, in order to get that circle to fit inside that square, there's going to be some distortion, some stretching somewhere. And that's what gets you this distortion right here. Is that discrepancy between a circle and a square. So the field flattener is actually kind of special. It reminds me, when I was doing research, of a neutral density filter. So let's go back. So you don't see the actual flattener in this particular diagram, but what happens is it'd be just a straight line that goes right here, right? And what it does, it flattens it. It makes it so that you don't get that distortion. Oh, and I should probably explain this. So Like I said, there's a lot of mystery with the Planar Lens. One of the mystery things, the lens, was what it was actually used for. So it was speculated that it's used for maps. It was used to map out the actual moon. All right. So what happens with maps is you need a very sharp image. You need to be able to zoom in, to be able to find different craters, the landing site for the moon. What happens is when you have blurriness in an image, right, and you get misinformation, your astronauts don't land where they're supposed to. That's a problem. So this lens is really special, is that it was supposed to be as sharp as possible, have as much light as possible, so that when the astronauts landed on the moon, they knew that where they were landing. It's my belief that it wasn't necessarily used for maps. And we could get into that a little bit later. It's a handheld camera. Like I said, the astronauts actually held it in their hand while they were on the moon. And most of those maps actually come from the satellite, which is a completely different camera, designed by Kodak. All right, so here you have different examples. Just this right here is what a Gauss lens looks like. This right here is the double Gauss, and then this is the Planar. So what happens is this would be considered two different lenses. This would be considered a double lens. It's because it's two different lenses cemented or oiled together to make one lens. And you see two of them. So, and then you see them stacked. So this would be one lens, that would be one lens. That's what makes it a Gauss. The fact that you have two would makes it a double Gauss. And then this cemented part is where the Planar comes from. Alright, so what you have here is the invention of the crown glass, named for Scott glass. Originally designed for microscopes, renamed Jenna Glass by Zeiss. So, okay, so Jenna Glass. There's actually another name for Jenna Glass, and you'll recognize this other name. What's special about Jenna Glass is that it withstands very high temperatures. Very, very high temperatures, because when you're in space you have super hot and you have super cold. The actual other name for this is Pyrex. Exactly, yeah. So it's the original Pyrex. The Pyrex before 1950 is actual Jenna Glass. And the reason why it's super important is the glass is what actually helps with remove the distortion. This doublet is actually made of two different glasses. It has to be. The first one is crown, and the next one is going to be flint, and they're cemented together, and something about that union is what corrects double vision for the actual lens. All right, so here's the shutter. It's a special shutter. At the time, is one of the fastest. It uses a piston. Shutters nowadays don't use this design, mainly because it has four different parts you see right here, which makes it slower compared to today's designs. But back then, this was super fast, and was important for the speed to go, and the NASA was reliable. It's not so reliable now. But what's important about this shutter is actually attached to the lens and not to the camera. All modern photography today has the shutter attached to the actual camera. And most of photography after this was invented, the shutter is attached to the actual camera. So how I was able to actually identify when this lens was used was based off of this particular camera. This was the only camera that NASA used that used this type of shutter. And so there's different documentation that will tell me the shutter and tell me the camera, but it won't tell me the lens. But the Planar is only compatible with this particular shutter.
What are the numbers at the top?
Oh, these?
Yes.
That's the timing for the shutter.
Fractions of a second.
Yeah, those are your fractions of a section,
Yeah.
second. Yeah. And then, yeah, it's completely different than nowadays. Everything nowadays is by button, it's turnstile, whatever. This one you actually have to, it's an extra knob that your fingers have to learn. It's crazy. All right, so this is the actual design. Paul Rudolph designed the lens, the Planar Lens, and it was first designed in 1896. So the design's from 1896, but it wasn't used really by Zeiss until 1966.
No.
Yeah, so it's kind of like I think of it like Leonardo da Vinci and the helicopter type of, 400 years afterwards type of deal. But it was just a good design. And the important thing about the halves and notches, I don't know anything about math. Like I said, I'm not a scientist. So the actual the shape of the lens determines how the light passes through it and all that. I don't know anything about that. But the different hash marks, as far as the drawing goes, tell you that it's different type of glass, right? So when you see the patents, I actually dug through some of the patents for these old designs. When you see the different hash marks, that tells you that there's two different types of glass being used in these patents. All right. So this is the Kodak lens. And what's funny about this lens was NASA actually, for their television stuff, for their satellite necessarily, the contract actually went to Kodak. And what happened with Kodak is that they did a two-camera system on the satellite. And one of the cameras failed. And then also, when the images came back for the other camera, they were horrible. They were dark, they were bad. So part of the reason why Zeiss got the contract is because the lens that was designed by Kodak wasn't good enough, right? But it's funny because even though that lens wasn't good enough and Kodak's designs weren't necessarily up to NASA's standard, Zeiss ends up stealing a certain portion of this design. So they beat out Kodak for the contract and then steal their design in order to make the new lens. Huh. All right, so yeah, this was just talking about the flint glass and how important the flint glass was. Oh, and why is this particular lens famous? So, why I chose this presentation for this specific presentation to choose the Planar Lens is I actually watched the video by Dan Savage. He's a huge fan of Stanley Kubrick, and he's a huge, he's a huge tech nerd. He's from Marygrove, huge tech nerd. He loves tech. And there's a really interesting video on YouTube about this particular lens. So, like I said, there was about 10 lenses made. NASA got 6. Zeiss kept 1. I don't know what happened to the other lonely one, but Stanley Kubrick, who knows how it happened, ended up getting the final 3 from the leftover batch. No one knows how he even knows those lenses even existed, where he got that information, but he ended up getting the final 3, and ends up using it for his film for Buried London. So, like I said, what's special about this lens is that it lets a lot of light in, and it can be used in very low light situations. And in Buried London, he uses it for the candlelight scene. Even nowadays, by nowadays standards, you could never shoot a scene with only candlelight. It's almost impossible. It's super hard. But he managed to do it with this particular lens in 1975. With no artificial light. So that kind of pretty much ends it. I wanted to really, are there any questions before from anybody?
Yeah, what was it that Zeiss stole from Kodak?
Oh, okay, so this is the condenser. Okay, so the actual lens, we'll go back to the design, because I actually want to talk more about the design, but it's kind of hard. So this is the actual lens. Like I said, the lens is a 50 millimeter lens, but this part, this actual lens is only 70 millimeters. So what happens is that at the, you guys work with telescopes. The reason why telescopes tend to be longer is that space in between helps the light bend. There's a certain point where the light bends back together, and that space helps the light, allows the light to do that. What happens with cameras is you don't have that space, right? You can't bring,
Right.
you know, can't haul a telescope to, well, you can, but you wouldn't want to. Haul a telescope with you on a boat, into space, something like that. So what happens is you have to figure out a way to shorten that gap, right? So what they did was they made a 70 millimeter lens and then put a condenser on the end that squeezes it down to 50 millimeters, right? And they stole this from from Kodak. They stole this from Kodak. This was in Kodak's lens. And actually the lens is only really, it's like a 1.4 is the original design, the aperture of the original design. But this adds more aperture and also makes it to where it can be shot at a 35 millimeter camera. And what's crazy about Barry, do I have it? Is the Barry Lyndon thing was that, I should actually use my notes. But the guy that he had to modify this particular lens, because this lens is designed for a still camera. And Barry Lyndon is for a movie camera. So a still camera is 35 millimeter, a movie camera is only 16. So in order to use it on a film camera, they actually had to break the shutter, right? And completely design a new shutter to use it on Stanley Kubrick's camera. And then what they did was they did the exact same thing. They add a condenser on back of the condenser to go from the 35 millimeter down to the 16 millimeter. So that's why this is kind of so genius, because the condenser they use is actually from a projector. They broke open a projector and used the condenser off of some regular projector and put it on the back of this lens, and then completely redid the shutter in order to use it for that scene. And then actually, it gave them more light. And there's actually he had 3 lenses. He got the one down, he got one of the lenses down to a 0.4 using another condenser. Yeah. So, any more questions?
Well, what about the composition of the glass itself? The silica, changing the molecular structure, temperatures, different temperatures, the source of the silica, are all these important things?
Yes, absolutely. So what's crazy about the glass, right, is that the glass actually changes the shape of the lens. One of the things I didn't talk about was the lens after this only uses flint style glass. But the lens before this uses the crown in the flint style. So I'm not 100% sure that the Planar doesn't use both flint and flint for its double lead versus the crown and the flint. And why I say that is because buried deep in NASA's information somewhere, there are banned substances. And one of the banned substances is zinc. And I believe the crown actually uses zinc in its composition in order to, in its glass composition. But it's a banned substance for the space station. So if they left the zinc in, this would be Zeiss's last lens to use both crown and flint. If they took the zinc out, it would be Zeiss's first lens to use only flint glass, right? And this is about the same, around the time that EPA standards are starting to come into play too. So you notice with their Tesla, the one after it, it has all flint because of new EPA standards that are going on at that time. And the crazy thing about it is, every time you change the glass, you have to change the shape. So the shape is dependent on the glass. The actual curvature of the actual glass is the curvature of the actual lens is really dependent on what type of glass you use and the combination of that glass. If you want to see it, I have the actual designs of the 4 prototypes, but I can't tell you what is flint and what is and how much of the difference the actual shape makes. I could show you different diagrams that show you how the light bends through the different shapes, especially the condenser. So like the original condenser, it actually looks like a crescent moon. But the problem is that crescent moon causes distortion. But I could actually show you the different crescents and how those affect the light that comes through it. But I couldn't tell you if that's based off of crown glass or based off of flint.
Okay.
So, but yeah, a lot of this stuff is, oh, sorry.
Did you say you think this planar lens may have been used by the astronauts on the moon?
No, it was. But
I think they're Zeiss lenses they
Yeah.
did use. I don't know if they used this particular one though.
right, what's crazy about this is the reason why I can't necessarily say what mission it was used on. I'm guessing it's used on Apollo 11. Like I said, there's missing information. So if you go on NASA's website, they'll actually name the different lenses for the different missions they used. But for Apollo 11 and I'll say 13, they don't name the lens. They don't even name the aperture. But for, I'm gonna say about Apollo 17, they name the aperture, right? So there's a lens after the Planar Lens that is a 2, right? It's a 2.0 lens, right? And they name that for Apollo 17, but then there's nothing for the missions before. And then you look even further back to the Gemini missions, they actually name the actual lens, which is a completely different lens and completely different brand for the Gemini missions.
They did use it, and it's still on the moon.
Yeah, so what happened was the reason why you can't, it's not in any museum, is that they dished it for weight. So $1 million lens, there's about 12 of the electric, the Hasselblad 500s sitting on the moon. Don't know, because only 6 of them are possibly be planar. But they ditched those $1 million lenses, put them on the moon so they could bring back moon rocks.
Go get them.
So, yeah, they're not, when I say I went into the Smithsonian's pictures and literally looked at every single picture and looked at the label of all the different lenses, you can't find it because it doesn't
I
exist.
think Jim Irwin brought his camera back, but it wasn't this lens.
Yeah,
The one camera was brought back, just one.
no, actually there's 2. And they
Oh, really?
actually they went to auction, and I think one went to auction like 2012. But what's crazy about that is it was illegal. The guy, I think, astronaut Gordo from the Mercury mission.
Kodak Cooper, yeah.
Yeah. So he brought back a lens, but actually had to be pardoned by President Obama for treason.
Yeah.
For treason.
For selling.
For stealing from NASA because it's a government project.
And otherwise, they were going to leave it on the moon.
No. He wasn't allowed to bring it back. He was supposed to bring back a moon rock instead. But he brought it back, and then 60 years later, gave it to an art auction. Mind you, I think it sold for something like $700,000, right? And it's not a planar lens on it. It's a different Zeiss lens. It's the Biogon.
Is that the camera and lens, or just like?
He got the camera, the lens. A Japanese, actually had the article. A Japanese guy bought it, camera, lens, and some prints. He still had some film left.
Oh, it was Dave Scott.
Yeah. There's 2 different guys. I could actually show you there's 2 different guys.
His got auctioned off in 2 years ago.
Yeah.
Yeah.
So Obama had to pardon him before, so he wouldn't go to jail for selling it. and, because it was treason.
Should've stayed on the moon.
Those Air Force guys.
Yeah.
Could you go back to the one where they had the 500 with the parts here, the original one? One of the earlier pictures.
Just
Whoa.
the actual camera.
Keep going.
The actual
Yeah,
camera.
right there. Because I actually thought it was like, I have Hasselblad, Mike also does. In fact, he's got one of the space special ones they made with a special covering, white covering, and everything, like a dedication.
Yeah.
Rian also does. The real genius of the Hasselblad, that was a problem in outer space, is that if you take a 35mm camera back in the film days,
Right.
you know, when you got gloves, you can't change film. Well, that back, the film magazine, those can be preloaded ahead of time, and they didn't have this size, but he did at that flight, but they had them larger backs. They used 60mm film, and you could go up to over 500 shots of film. So you could take 500 pictures, little button at the top, you push a button, comes off, put another one on. On the left, there's a little, it's like a D-ring, a little piece of tab on the side, and that slide goes in so you can remove that back, and you can put another one on. So the real genius of it was that you can easily change the back with gloves on.
Yeah, what's also special about the film, and I didn't mention this, like another Kodak moment, was that Kodak actually, they had a special film. So Kodak actually made some extra, like some sensitive film. Before this, I forget what the actual ISO was, but their film was more sensitive.
Also, it was very, very thin.
Right, it was very, very
Get
thin
more
that
shots
allowed
on the
them to
wall.
actually use this
Yeah,
camera.
yeah.
Before that, they wouldn't have been able to take those
Yeah.
pictures. So Kodak didn't get the contract, they still use Kodak film and they still use Kodak design. Yeah. Any other questions? Other random facts about this was that the reason why that I believe that this was used on the Apollo project was the amount of money that the Apollo project did compared to Gemini. I got some different figures, but I think the Gemini was only like a few million versus Apollo was closer to like $500 to $1 billion or something like that. So there's a lot of speculation that this was actually put on a satellite, but there's a picture. Can I show the picture? The first picture is the actual harness that they designed that uses. So this top one is actually, I think, the television camera. And then this bottom one down here, I believe, is the Hasselblad. And there's a special harness, and I have another picture if you guys want to see it. I have a bunch of stuff, but they didn't make the presentation of the actual harness and them practicing to use it when they went on.
So, does Stanley Kubrick's estate still have all three of the lenses that he had bought?
The collection, yes. And actually, what's interesting about it was the reason why Dan Savage did the video. There was a museum exhibit in San Francisco, and then a few years later, you could actually rent those lenses now. I don't know how much it costs to rent those lenses because there's only 3, but they retrofitted them to fit on like a red camera or something like that. And you could actually rent those. There's only 3 in the world. You could rent those lenses. So yeah.
It's kind of ironic given that Kubrick refused to ever rent lenses, which is why he ended up buying all these lenses.
Yeah. Yeah. He there's an interview, not with his cameraman. And so the actual camera that he used in that, there was only like 2. So he completely destroyed this camera, and there's only like 2 in the world. And then he completely destroyed the lens, and there's only 3. You know what I mean? Like he just when he wanted to do something, he just did it. He had the money, he had the means, he had the know-how. Yeah.
Is there more light on Mars than there is on the moon?
I would say no.
It's a nice shiny surface.
I don't know. It depends on a lot of things because you're talking about light bouncing off of other planets, and then you're also talking about Yeah, I honestly don't know.
All the pictures we get are pretty much natural light.
Yeah, but you gotta understand, cameras nowadays, they didn't make better lenses, they don't make better lenses nowadays, what they have is better sensors.
Yes.
So the sensors make up for that lens. So like ISO on a like I said, film is 400. For my little camera, it goes up to 16. For other cameras, I've seen it at 32. I think the red is just ridiculous. They just keep adding zeros. So the lenses didn't necessarily get better. What happens is the sensors got bigger and got better. There's the new satellite, the Tesla satellite? It has 4 lenses, and the sensor on that is the size of a record player. And its sensitivity, it's the most sensitive lens. It's the most sensitive sensor made ever. So the lenses are about, I think they're less than the 0.7.
What?
I think those lenses are less than the 0.7, but it doesn't matter because the sensitivity of that sensor makes up for the light coming through that lens. Any other questions or? Sorry I wasn't more specific in the details.